packets on winds and jet stream, the Coriolis effect questions, some of the questions about El Nino. And really this kind of helps us understand how hurricanes move around the world, move around the globe. So let's go get started here, and hopefully this will kind of help you with your homework and give you a good preparation, if you will, for our quiz. All right, let's take a peek here. So where is St. Louis? St. Louis here, this little green dot. You can think of St. Louis as about, I don't know, we're about 40 degrees latitude or so. I think most people would understand if you just look at our Doppler radar maps, look at our weather maps, you would say that in general, our wind, our weather, is coming from the southwest. So we live in this area of the globe that are called the prevailing southwesterlies. Now, to kind of remember these prevailing wind patterns all over the globe, what really helps me is to just think about where the wind is coming from in St. Louis. So that is coming from the southwest. And then really the only other thing I remember is what the doldrums, or what the equator really is. And this is also called the International Tropical Convergence Zone. Let me share one of my favorite stories growing up. I don't know if you've heard of the Cyrus, the unsinkable sea serpent. But anyway, so Cyrus was a little mischievous, and he was going to play and kind of disrupt some of these boats that were looking to sail across the world. But then kind of once Cyrus got to know some of the people on the boat, he ended up helping them out. But as the boat was leaving, an old man standing at the side of the shore said, "You're in trouble. You'll never make it. You'll run into the doldrums and be stranded forever. If you don't hit the doldrums, you're going to hit a storm and it will take you under the sea." All right, so anyway, and look, I mean, there's so much surface tension, so much cohesion in that water. I mean, Cyrus is able to just scoot along on the surface. All right, anyway, so what happens? Well, sure enough, the boat sailing across. "They've been hornswoggled," growled the captain. "We've run into the doldrums. We've hit a dead calm. What will we do?" Well, Cyrus, ending up becoming a helpful, a friendly sea serpent, blows their ship out of the doldrums. So think of the doldrums, think of this International Tropical Convergence Zone, and it is right around the equator. Think of that as where there's really no wind, or very little wind. And if you remember that, it's because it's kind of easy to look at these arrows, how they're canceling out. And it's kind of easy to see how these winds would converge here at the doldrums and kind of cancel out. And it's that effect that really helps explain also the Coriolis effect a little bit, but really also why hurricanes and big storm systems don't stay organized as they cross through the doldrums, as they cross through the equator. If you were worried about Cyrus, don't stress. Like I said, he he blew that ship out of the doldrums. Now, unfortunately, he blew them right into, really you could think of where it's very windy and where a lot of ships would even sometimes try to get into these horse latitudes, because really that was where they would sail quickly across to the New World, quickly across to the United States. So yes, you can get around quickly on the ocean in the horse latitudes. And if you look at the prevailing wind patterns, these red arrows, you could see where a lot of wind is kind of starting or originating from there in different directions. And that's kind of an easy way to think of a big storm. So you can see this big cumulonimbus cloud forming here in the sky. So after Cyrus blew the ship out of the doldrums and into the horse latitudes, they hit the storm, but Cyrus decided to kind of save the boat there from crashing. Okay, so anyway, an easy thing to remember this kind of global wind pattern is just remember what St. Louis is doing, southwesterly winds. Remember the doldrums, and then from there it's pretty easy to put this pattern of arrows, pattern of prevailing winds together. So that's what helps me. And please, yes, I do want you to know the doldrums as really right near the equator. It's also called the International Tropical Convergence Zone. And certainly I want you to know where St. Louis is on here, about 40 or so degrees latitude, and we are in this part of our globe with prevailing southwesterly winds. Okay, now when you think about or look at our jet stream on a normal day, a normal year, if you will, so on a normal year, we kind of have this one pattern of air moving through our jet stream. Now, the jet stream, it's different than surface winds. The jet stream is really winds, or kind of movement of the atmosphere at a higher level, not necessarily down at sea level, not necessarily down where we feel the wind. The jet stream is going to be up in the atmosphere a little bit. And as you climb in altitude, we know there's less air, which really means there's less air pressure as well. So as we climb up, and that's really where the jet stream is, there is a lower pressure. Remember, pressure we can write in inches. So we really say about 1,000 millibars is about 30 inches of pressure. And then as we climb or go up in the atmosphere, the millibars, the pressure readings do decrease. And really just going up like 5 miles, it gets cut in half or even more than half. So if you were to take a barometer that measured inches 5 miles up, it would go down about halfway, if you will, or even more. So the jet stream is really kind of upper level atmospheric motion. And this is kind of typical, kind of normal jet stream pattern. You can see a little bit of that southwesterly flow kind of coming across St. Louis, kind of coming across our United States. Now, the temperature of the ocean has an impact on this upper air movement. And really for our purposes, I just want you to kind of understand that El Nino really refers to some warm water, really warm water kind of southwest of California, kind of off the coast of Mexico here. But we get these warm water regions, and as that warm water kind of collects out here in the Pacific Ocean, that does influence our jet stream. So the thing I want you to be able to look at is this picture where we have this jet stream up through Canada, and then another jet stream kind of moving through the southwest up into the eastern part of our country. This is a typical pattern for what we're experiencing right now. So we are on, last year was an El Nino year. My understanding is we are at the kind of a tail end of the El Nino events this year. But this would be on a typical day, kind of the pattern of our jet stream during an El Nino year. How does that affect St. Louis? Here we are. Yes, we're going to get more stormy weather, more wet weather coming our way as a result of an El Nino year. And once again, just think of El Nino as warm ocean water, kind of down near Mexico, down near kind of southwest of California. All right, so as this weather and as this air is moving in, some simple ways to kind of predict what's going on. Now imagine you are standing, I guess a good way to think of this is imagine you're just kind of facing north is fair, and this storm is blowing to the east. So imagine this is kind of, this whole picture is moving to the right, moving to the east. The blue is colder temperatures. The red are warmer temperatures. So if you're standing, I don't know if you can see my cursor, but if you're standing over here on the right in the cold air, and you feel a warm breeze, so you feel some approaching, this warm air mass is moving towards you if you're standing here. You could call that a warm front. It's fair to think of that, just an air mass as a front. So we got this warm air moving towards you. If conditions are right, if dew points are correct, and humidity levels are kind of set for water to start condensing and falling and raining, if you feel warm air, a warm front blowing into you, and it's going to rain, that approaching rain will be due to stratus clouds. So really what's going on, you'll see some cirrus clouds kind of come overhead, and that's a pretty nice day still, pretty nice temperature, pretty nice dry air if you see these cirrus clouds up here. But then as that warm front starts to approach, those cirrus clouds may start to get layered and become stratus clouds. Those stratus clouds may sink a little bit and become altostratus. As they get more and more moisture and get darker and darker looking, we could call them nimbostratus clouds, and they could start to produce rain. But now, rain from a nimbostratus, you're not going to have to. I mean, we play baseball sometimes when it's sprinkling here with the nimbostratus clouds. You can be outside when it's raining. This is not a severe weather event. So this is not going to be thunder and lightning, storms, hail, tornadoes. So in general, if there's an approaching warm front, this would be the cloud pattern you would see, which could result in precipitation, but just not severe weather. Now, imagine for a minute you're standing here in the warm air. So it's nice and warm out, woohoo, nothing up in the sky. All of a sudden you start feeling this cold breeze coming at you, this cold front approaching. An approaching cold front we see will allow cumulonimbus clouds to pop up and to show up. Just even yesterday, I mean, we had hail around in our area yesterday. There was a lot of lightning and thunder during seminar. And really there was nothing. Check the radar, the sky wasn't that bad, but then this cold front came in, these cumulonimbus clouds popped up, and those are the ones, if you remember, those are the severe weather events. Now a hurricane, really all that a hurricane is, and in fact if you just kind of take an overhead view of a hurricane or something, that's just a giant cumulonimbus cloud. All right, a cumulonimbus cloud over the ocean is what that is. So hurricanes are really nothing more than a cumulonimbus cloud over the ocean that is starting, that kind of organizes itself, and then those pictures we see of it, we can kind of see a lot of that swirling and spiraling effect we'll talk about. Oh, this is just out my bedroom window the other day, but you could see, this was kind of shortly after school, about 4 or 5 o'clock, but I know you probably have seen the sky look like this, but you can see, when you see this sharp, distinct line, really it's just a function of how the sunlight is reflecting and refracting and diffracting through the sky. But when you see these sharp, distinct lines in the sky, a lot of times you can see these approaching fronts that way. And a lot of times these approaching fronts are influenced certainly by the Mississippi River, Missouri River, and you can kind of peek out that way and see those fronts following those large rivers that we have in our area. So yeah, I just kind of thought, kind of a fun picture, once again, out back Mr. Watterson's house. This is facing north, but once again, you see these distinct lines in the sky. A lot of times that is where these air masses are separated, and you can kind of see that line yourself with your own eye. Okay, so, but once again, an approaching cold front, storms. Approaching warm front, could rain, but not severe. All right, now peeking at weather maps. You've seen a lot of these H's and L's on weather maps. So the H stands for high pressure. The L's stand for regions of low pressure. Now I kind of really liked these pictures. It's kind of, if we had to average out all the pressures, just kind of take a typical day, if you will, in January, and then the bottom graph is just kind of a typical, your average day in the summer, in July. Couple things I want you to kind of peek at. A typical day in January, we have high pressures kind of centered over Canada. All right, and this high pressure, the air will spiral clockwise in the northern hemisphere. A lot of this cold air that we get in January is kind of a result of this high pressure situated over Canada, and it will spiral down and boom, boom, boom. So this is kind of a typical January day. Now, if you look down here in July, what do we see in the United States? Well, there is a low pressure centered over like New Mexico, kind of Arizona, right there. Now that low pressure system actually spirals counterclockwise. And so that is pretty typical of our weather. If you look at that counterclockwise spiral of the low pressure, that can contribute to bringing in a lot of this moisture from the Gulf, some of this moisture from the Atlantic Ocean. And then even kind of depending upon how that low is centered, it could even pick up moisture from the Pacific and kind of bring it into our area. But on a typical July day, there's a low pressure centered over New Mexico. On a typical day in January, there's a high pressure kind of centered over Canada there. All right, now, a thing I want to kind of look at is, this really happened yesterday, but it also happened the same week last year where we started to get some severe weather this first week of April. So I know some of you were outside kind of looking at the light, thunder and lightning yesterday, or maybe out your window during seminar. Last year during this week, there was just a massive hailstorm. So here's some YouTube from that. You can hear the tornado sirens going off there too. But I remember it just went dark. This was during school. I was teaching, and it looked like it was nighttime outside. Now this is a few miles west of school, is where this size hail didn't hit us. So this was like out in the Parkway School District, is really where this picture was taken. But yeah, that was one of the craziest storms that I have seen. And like I said, our area, we didn't get this big a hail, but it was a lot. It was really, really super dark that day. Crazy, crazy day last year. So here was kind of a screenshot of the Doppler. Now really, this, you can see this red. We kind of know red is faster moving water. There's more moisture in those red regions. But yeah, but that red is really right where that hail was kind of starting to move into our area, if you will. So let's peek here. What's going on with that? This is what kind of made that so crazy. It was 60 degrees outside, and we got the giant amounts of ice just falling from the sky. Now, remember, think of hail as really just pieces of a cloud that have just fallen and deposited themselves right on the ground. All this instability in the cumulonimbus cloud, all that wind really just breaks off pieces of the cloud, and this water is kind of melted, froze, and started. That cohesive property of the water is what allows all that to stick together. And a great way to think of hail is it really is just pieces, frozen pieces of a cloud that are just falling down and falling on the ground. So what's crazy about this, if you look at it, the wind on the surface here was coming from the east or the northeast. But the storm itself was kind of moving. It was in that prevailing southwestern flow. So the storm, if you watched it on Doppler radar, would move this way. But the wind was coming from the opposite way. And that's kind of that shearing effect, that wind on the surface moving one direction, the storm moving the other direction. And that's kind of what contributes to that instability in the clouds, and then just those clouds literally falling and the hail falling on top of us. So it's crazy. East wind, so wind coming from the east, but the storm itself is migrating or moving, that way. So it's kind of weird to think about. You have a storm moving in the direction the wind is coming from. Crazy, absolutely crazy. But that is really due to this storm is going to be where the low pressure center is. That low pressure has spiraling counterclockwise, which is what that wind was that we were experiencing or feeling. So let's look for that low pressure. Here's that. Now, once again, this screenshot's it was from the time of the storm, but this low had really kind of moved a little bit, this low pressure center a little bit from the time that it was displayed on the Weather Channel. But anyway, low pressure, counterclockwise spiraling. And it's that spiraling, boom, that was hitting, that was allowing that east wind to hit us, even though that storm system was moving in the opposite direction. So if you look at the temperature map, here we were about 60 degrees, and it was hailing, but you can see here's this big cold front on the western part of our country. That's the approaching cold front. So if you go back to this picture here, this approaching cold front we will feel it's the cumulonimbus cloud moving in. So if you look at the isotherm map, just this, warmer temperatures, colder temperatures, this approaching cold front This cold front in that part of that southwest flow up, that approaching cold front is what is characteristic of a cumulonimbus, a big storm cloud approaching. If you remember where that low pressure was centered, so if you go back to the original map, here's the L, here's the low pressure system, here's this approaching cold front here. But this low pressure is going to have counterclockwise spiraling. Look at the wind pattern from that day, and you can really see the way we've kind of diagrammed the wind, as you can really see that counterclockwise. And really what it is, it's just the air spiraling into that low pressure center. Remember, air will always move from high to low pressure. If you have a low pressure center, that air is going to spiral into it. When do we see it? We don't actually really see it until we look at the moisture. But another thing that really kind of helps us predict the weather is if, remember, the dew points and temperature are close, that really means that atmosphere is holding as much moisture as it can. When that air can't hold any more moisture, it starts falling out, starts dropping on the ground. But yeah, so when you see deep dew points at 61, current temperatures at 63, when they're real close, that really means the air is fully saturated and is holding all the moisture that it can at that temperature. Okay, so let's take a peek here try to at least kind of explain this Coriolis effect, which is really quite profound. So here you can kind of see, I love this picture, you can see the curvature of the earth and outer space in the background. And you can see all of the storm system organizing over the ocean, and you can see this would be the low pressure center. Now the eye of a hurricane, that's not the same as the vortex of a tornado. Please don't think they are. This wind actually, even though it's a much more larger scale, this spiraling wind is not nearly as fast as a tornado. All right, remember this. Some of those vortexes kind of occur locally on a smaller scale with much more damaging and faster winds. This is kind of, remember, here's the world, here's the globe. So tornadoes aren't that size, aren't that width in diameter. So the physics of it are kind of the same, but don't think that this wind is not as fast as a tornado. But you can see the low pressure center. And here's a really good view. You can kind of see how all of this is spiraling into the low pressure center. You can see Cuba here, Florida, but I love these satellite images where you can really, the way the light is refracted through the moisture, you can see that counterclockwise spiral into a low. So what do we say? We try to kind of set up a little demos in our room so you could see the Coriolis effect. But on a simple level, we have this fast moving air. Even though it doesn't feel windy, the air at the equator actually moves. The air masses at the equator actually move faster in order to rotate with the Earth. And that is going to pull air into the equator there. So we kind of had a fan set up in the middle of our room, and it was a kind of a decent model of how air could be pulled into there. And that's what we see. So if the air is heavy, if it's a high pressure, if the air is sinking down towards the ground, high pressure. Now remember, high pressures are like cold air, dry air. Those actually are higher pressure. Those are high pressures. Cold, dry air is the highest pressure air we have. But that feels nice outside. All right, it's crisp out. People say it's good weather when there's high pressure systems. So if this pushes down, what we see happening is when that pushes down, high pressure systems spiral clockwise in the northern hemisphere. Low pressure. Now low pressure, remember, is like a lot of water, warmer air. Typically, we all kind of know warm air will rise. Cold air will sink. Moisture, water, when you start cooking and stuff and getting steam, the steam's going to go rising. So when there's a lot of water, water is actually a lighter weight molecule than like oxygen, nitrogen, than carbon dioxide. So when there's a lot of moisture, a lot of water, we say that's a low pressure. When there's a low pressure, we see that counterclockwise spiral around that low here in here in the United States, here in the northern hemisphere. So this is a low pressure center, would be right here at the eye of the hurricane. And we see it spiraling counterclockwise into that low here near Florida, here near North Carolina, here down here near the Bahamas and Cuba. Okay. Yeah, you can kind of observe it. We tried. Let me just show you a couple things. First of all, remember water is low pressure. So other types of air actually sink and kind of apply a higher pressure. So even if you kind of remember, this is carbon dioxide. You can see it, even though it's kind of jumping up out, it still wants to sink or fall back down there. So here you can see it doesn't even really want to escape out of the bin. All right, we just kind of let that dry ice. So even if we try to get it to move away, it still would just sink and kind of fall to the floor. We knew it was very cold air too. That cold was sinking and kind of falling to the ground as we tried to get it. So here's another one. See how this goes. But yeah, you can see a little bit of the rainbow, the diffraction effect there. But yeah, but even those clouds there, if you remember, they would fall right off the bin, fall off the table. They would push down. So the dry ice is kind of a way to kind of think about the sinking air, the high pressure. So that cold air would always try to sink, and you could watch it just fall off your table and fall to the floor. Okay. Now, the other day, I don't know, maybe I was cooking some food. So here I am at my house again. All right. And I thought this was pretty neat. This was just kind of an accident. I had to just go film it for us. I was throwing some salt in. I was getting ready to cook some noodles. But look at the water. I don't know if you can see it. It's a little skippy on the internet here. Ooh, there. Do you see it? There, let me try to play another one. But that hot water, that steam, and we even kind of saw this when we dumped a bunch of steam on our tabletops in the room. But watch the steam here. Watch the steam. There's a little bit of salt in there to kind of help that. Here we go. I put some salt in so you can kind of see. But I'm not stirring it. I'm not doing anything. But as that steam is escaping, you can see a little bit of that counterclockwise motion there. And that is, it's just crazy to think that I'm cooking macaroni and cheese and that spiraling of the rising steam, that spiraling of the rising air is this. So like, how in the world, here I am in St. Louis cooking macaroni and cheese and my steam starts to spiral counterclockwise. Here I am taking a picture from the satellite in space and this water vapor these clouds start to kind of organize and spiral counterclockwise. It's quite profound. And a lot of that has to do with those special or unique properties of water. We do know that water takes a long time to heat up. It takes a long time to cool down. We say water's very cohesive, it sticks together. We say water floats. That's all kind of crazy, crazy stuff. It's weird that we can have, solid, liquid, gas all in our room, all in our atmosphere. That's very unique. And then just the way water looks. It can look so many different ways. It can look white. It can look green. It can make a rainbow. It can just have all these different effects that we see in the sky. And that really kind of contributes to our image of weather, what weather looks like when we take pictures of it. So yeah, please remember and kind of think about these special properties of water. That's kind of been a big theme of our course. So hopefully you've looked at this understanding sky and light vocabulary. I do plan to kind of give you this same picture on the quiz. Where is the light reflected? Where is the light refracted? Where is the light absorbed? So hopefully you've peeked at that and made sense of that. But really, you guys, I just thank you for all your time on this. It means so much to me. I really think that just wondering about what we all experience, what we all have in common, is something that you can talk about with anyone. You can share your stories, share your adventures, share your experience with the weather with anyone, anywhere, anytime. And it's a great way to just, for job interviews in the future, meeting people in college. You can always talk about the weather because you always have that environment in common with everyone. In fact, I don't know. I was very kind of inspired by Dr. Green's visit to our school. He's come a couple times as a distinguished alumni to speak. But he's a director at the NIH. Oh, I mean, just really one of the most, well-respected scientists in the whole world, not just here in the country. He's a Horton Watkins graduate. Some of the things he said when he was here, he said, I was an average science student. He said he got B's and C's in his science classes. He was in band, he was on speech team. But the big thing he took with him from going to high school here was that he learned how to communicate and how to think. Um, and once again, with this course, this weather course, if you can communicate about what you see outside, once again, you can talk to anybody, anywhere, and that's a skill that could take you on to bigger and better things once you graduate. So thank you for all your time. I, um, I'm glad you listened. And when Dr. Green was here, or about the same time, our school performed Into the Woods, which I don't know if you like that play. It's a good one. So anyway, thanks again for all your time, you guys. I really appreciate it.